redrawn the S&R latch here that we were talking about in part 1 here. Here's the truth table for the S&R latch. I've dropped the NAND gate truth table. We're going to need to know it, or if you would like to keep that handy, you can write it down. But for these purposes, trying to save board space, we're just going to work with this. Alright, so the S&R latch, we saw foundationally, I'm going to add Q and Q not, like we had before. You saw how foundationally this works. It works by, you can set a 1 for data on Q, you can reset a 0 for data on Q, and you can latch it by doing 1-1. And when you go to 1-1, states stay the same. So whatever it was previously will stay. Q and Q not will not change. Alright, so this is the basic foundation for 1 bit of storage. Okay, well, I'm going to add something to this. We're going to figure out a way to make this a little easier to use. So what we're going to do is we're going to tie 2 more NAND gates to this. Alright? And we're going to label one of their inputs S and R. And we're going to tie the other 2 legs together. We're going to call that an enable. Now, they can also be referred to as a debounce circuit, which is basically the same as an enable-disable function. Alright, well, this makes the circuit a little easier to work with, and I'll explain why. Alright, because of the NAND gate properties right here, if enable is low, we are going to hold, and remember, enable, these are all 2 input NAND gates. All we're using is NAND gates. If we hold a low, a logical 0, on one of each of the inputs of the NAND gates, this is going to hold the outputs of these 2 NAND gates, and let's label them, we'll call them G1, G2, and our S&R latch, we'll say G3, G4, just for better identification purposes. So if the output on G1, G2 is 1 and 1, then remember back when we were talking to the basic S&R function, if we have a 1 and a 1 here, we're in a latch state. So again, if enable is low, has a low on it, a 0, this is going to put the S&R latch right here in a latch state. And that just basically means that whatever was on Q is stuck there. It's holding it. It's data being held, memory. Alright. If we take this and put a 1 on it, we now allow normal operation of the S&R latch. It's almost like as if these gates weren't even here. You can set a 1 on Q with a 0, 1, or you can reset a 0 on Q with a 1, 0. So again, this circuit right here uses gates as they were meant to be used, as gates. With the enable taken low, it keeps a 1 and a 1 here, so whatever's on S&R doesn't matter. It puts the NAND gate, or sorry, the S&R latch in a latch state. But if the enable goes high, of course, just erase the 1 to put it back, the enable goes high, and whatever's on S&R is going to pass straight through to the gate, to the S&R gate. So really, this circuit right here is like a gatekeeper. If it's high, whatever's on S&R will be passed to the latch. If it's low, it is going to latch this part of the circuit. It'll provide the 1 and the 1 that it needs to stay in a latched position. So, it makes it easier because now we have a logical enable-disable. Whenever we want to pass data to Q, we keep a logical high on the enable input right here, and whatever we send on S&R will make it through to the actual latch. If we want to store the data that's already on Q, then we take enable low, which will put a 1 and a 1 on the output of G1 and G2, and latch the S and R.